about the video coding standards, and instead of spending time with the earlier standards, okay, we will just make a very quick reference and go over to the H.264, which is the latest in the standard. So, I will be covering mostly H.264 in details in this lecture, okay. And just before coming to H.264, we have to make some passing reference about some of the concepts of video coding, which is which has been already done in the previous standards. So, we will take some reference of the previous standards and then talk about this. So, let us now come to I mean one or two very important aspects of the video coding. You see, we have already told you that basically when you have a video sequence, okay, then the sequence is essentially partitioned into a group of pictures. Okay. So, we can call those group of pictures by the name GOP. So, we start with the GOP number 1, then GOP number 2 and so on. Okay. So, so there will be a group of pictures which I had said that will consist of, I mean if you just take the composition of any GOP, you will be finding like this, that there will be an I frame, okay, followed by there will be some B frames, there will be some P frames in between, okay. Again it will have some P frames and more number of P frames and B frames in between. So, this is how the GOP structure will be there. Okay. This also we have discussed. Now, every such frame, okay, these are all the frames, individual frames, every frame is actually partitioned into a set of slices. Okay. Let us say we just look at any particular frame, where we will be having this frame partitioned into various slices. So, slice number 1, slice number 2 like this. So, where slice will be a part of the picture, like say for example, if this is the frame, okay, then one can divide it into, let us say 3, 4, 5, say I mean this is the picture. So, 3, 4, 5, 6, 7, 8. 8 slices we have partitioned. Okay. So, like this slices are actually some sub parts of the frames, okay, for which a specific data structure is defined. Okay. Now, when we look at the composition of the slices are composed of some macro blocks. Okay. And what is macro blocks? Macro blocks are basically composed of a group of blocks. Okay. So, macro block actually is partitioned into blocks, okay. And block size, you already know that block size for all the initial standards we have been taking the block size to be 8 by 8, but only in the most recent one we are having the block size as the variable, and it can be as low as 4 by 4 block sizes. So, macro blocks are composed of blocks, and I will now tell you that how these blocks and macro blocks are related. Basically, if I take every block to be, let us say 8 by 8 size, okay, then what one can do is that whenever one is having a colored image, okay, we take see the color image can be represented in two formats. One format is the RGB. Okay. In the case of RGB format, what we do is that we allocate 8 bits to each of these color planes. Okay. 8 bits for R, 8 bits for G, 8 bits for B, where we will be having essentially 24 bits per pixel. Okay. But for the RGB, the I mean information pertaining to the color as well as of the intensity are all embedded within. Okay. There is no separate information for the color or no separate information for the intensity. The R, G and B values themselves contain the intensity as well as the individual color planes. Now, there is an alternative representation which is done, and that representation is the YCRCB structure, okay, where Y is the luminance, okay, which basically indicates the intensity values, and CR and CB they indicate the chrominance values. Okay. So, the luminance chrominance representation's advantage is that luminance chrominance information actually takes you the intensity and the color parts as separate ones. Okay. So, now what happens is whenever we are having such luminance chrominance representation, YCRCB representation, or it is sometimes referred to as the YUV representation. In the case of YUV representation, we take a 16 by 16 block size, okay, so, I mean a group of 16 by 16 pixels. So, where let us say that it is like this, and this 16 by 16 size which we call as macro block, okay, every macro block will consist of a luminance part of 16 by 16 pixels. Okay. It consists of luminance of 16 by 16 pixels, and if our block size is of 8 by 8, then every luminance macro block is going to have 4 blocks, right. So, I can partition a luminance macro block into 4 luminance blocks. So, each of these will be of size 8 by 8, these are the blocks, and we have 4 such blocks, right. And other than the luminance, we also have the color components, the CR and the CB. Okay. Now, it is seen from the psychovisual experiment that that our eyes are more sensitive to intensity as compared to color, and as a result of which we need to preserve the resolution in the intensity or the luminance space, and we need not have to keep that high resolution for the color space in comparison. And the color components can in fact be subsampled by a factor of 2 in both horizontal as well as vertical directions, meaning that only 1/4 of the size as compared to the luminance values are enough for the viewing of the color components of the picture. So, that corresponding to a 16 by 16 area in the luminance image, we can subsample the pixels by a factor of 2 in horizontal and vertical direction, okay, and by subsampling this 16 by 16 will be converted to an 8 by 8 chrominance, and it will also have an 8 by 8 chrominance red and chrominance blue components. So, we have essentially 6 blocks, okay, 6 blocks of size 8 by 8, 4 blocks corresponding to the luminance, okay, and 1 block corresponding to CR, 1 block corresponding to CB, and this we can only do because the because in the color space we can subsample by a factor of 2, okay, without affecting the psychovisual performance. Okay. So, I mean making use of this psychovisual redundancy aspect, okay, it is possible to have a representation like this. So, this is the relationship between the blocks and the macro blocks. So, this whole thing will be a macro block consisting of 6 macro block of the YCRCB image, okay, consisting of 6 different blocks, 4 of luminance and 2 of chrominance like this. Okay. So, having known this structure, now it is very important for us to see that how do we encode every macro block. First of all, that why are we having this type of a structure? You see, whenever we are encoding a video frame, all right, there what are we doing? Essentially, the important thing what we do is to quantize the transformed samples, right. So, whenever we are quantizing, then it is very important to note that what should be the extent of quantization, or rather there should be a quantization parameter which should be specified. Means if we have a quantization matrix, okay, in that case what quantization parameter we use, that will depend upon the coarseness of the quantization, whether we want coarse quantization, in which case we have to use larger values of the matrix, we have to multiply the matrix elements, quantization matrix elements by some constant factors, okay. Whereas if we want finer quantization, then we need not have to multiply this. So, so this quantization parameter, this can vary from macro block to macro block, because it is 16 by 16 area. So, if we have an image, okay, let us say that this is an image what we have, okay. So, what we do is that this image is partitioned into a group of such macro block. So, these are all the macro blocks, okay, to which this frame is subdivided, and within this macro block we will be having the blocks in the Y, CR and CB planes. Okay. So, now for if now whenever an image is there, it is not that the details is present uniformly over the image. There are some parts of the image where more details are present, okay, where we have to encode that with a better quantization factor, finer quantization factor. There are smooth regions of the image where we need to encode with coarse quantization factor will be good enough. Okay. Even whenever we are encoding the motion also, okay, or rather the motion predicted image, whenever we are encoding the difference between the incoming and the motion predicted image, there also wherever more amount of motion is involved, there we have to do finer quantization, wherever less motion is involved we have to do coarser quantization. So, that is why in essence what I mean to say is that from one region of the image to the other, the extent of quantization can vary, and that is why each macro block is going to have a different quantization parameter. Not only that, not only the quantization parameter for every macro block is important, one also has to specify the mode of the macro block. By mode of the macro block, I mean to say that, as I was mentioning, that there are some macro blocks which do not undergo any significant change, but there are some macro blocks which are undergoing very significant change. For example, that supposing we have an image where in frame number 1 we do not have a particular object, but in frame number 2 a particular object has appeared. Say this is the part of an object which has appeared in frame number 2, but it was not there in frame number 1. Now, that means to say what? That means to say that in frame number 2 we have got some new information which has come in. Okay. So, what if we try to do it as the simple inter frame coding, okay, taking the frame 1 as reference? How about doing the motion estimation and finding out? Well, for those areas where it was visible, where the object was visible in frame number 1 and in frame number 2 it is displaced to some extent, yes, for that you do not have, for those parts of the image you do not have any problem in finding out the motion vector. But for this region where you are having some new information, how can you obtain correspondence? You will try to obtain some correspondence, you will try to obtain some minimum of sum of absolute difference and find out a motion vector, but that motion vector is going to be erroneous definitely. So, which means to say that if you are trying to predict an image based on that motion vector, you will be observing large amount of error, large amount of prediction error. Now, depending upon the prediction error from one macro block to the other, you can decide that whether that particular macro block you are going to encode at all with inter-frame coding, or whether you are going to treat that macro block, treat that part of the image like intra. Intra means without any past reference frame. Okay. So, in the mode of the macro block, you can define some macro blocks as coded in the intra mode, and there will be some macro blocks for which you are finding the correspondence in the previous frame. You can encode them in the inter frame. So, there is intra frame prediction, there is also inter frame prediction for every macro block. Okay. So, it is not essential that whenever we are encoding a particular frame as the P frame or B frame, okay, then all the macro blocks pertaining to that picture has to be inter coded. Never think like that. The frame can be a B frame, the frame can be a P frame, but some of the macro blocks could be intra coded macro blocks, some macro blocks, majority of the blocks may remain as the inter coded macro blocks. Okay. Even in the inter coded macro blocks also, there are some situations, okay, which will help you in saving the number of bits. You will be finding that there are some parts of the image where there is no motion that is involved, okay, but there is some change in the contents. So, in which case what happens is that the motion vector is 0, whereas the content has changed, content in that particular area has changed. So, you can say that in those areas, okay, you will not be sending any motion vector, but you will be only encoding the frame to frame difference, okay, for those macro blocks. You may observe, like for the background macro blocks, the macro blocks which correspond to the background region, like say for example, in this frame what you are viewing, okay, the background information, the background is a color, that is what you are finding. Okay. Now, in that background information there is no change from one frame to the other. So, in those macro blocks, the macro blocks which correspond to those region, it is neither having any change in intensity value, nor is it having any motion vector. Motion vector for those macro blocks are going to be 0. So, best thing what you can do is that you can skip encoding those macro blocks. So, there is also a skipped mode that is defined. So, mode of the macro blocks could be inter, intra, skipped macro block, and within inter also there is a variation, that whether you want the forward encoding to be on, whether you want the backward encoding to be on, I mean forward prediction to be on or backward prediction to be on, all these different modalities are possible. So, essentially this is how the mode of the macro blocks is going to be defined. And now, with this concept I come to the latest latest video coding standard, which is the H.264. Now, mind you, in the conventional way of motion estimation, how are we representing the motion vectors? Naturally, we are taking one of the we are taking the current frame. So, we are going to predict the motion corresponding to the macro blocks or the blocks in the current frame with respect to the previous or the reference frame. So, there is a current frame and there is a reference frame, and for every block we are finding the motion vector by consulting the reference frame. Right. Now, in such kind of cases, whenever we are indicating the motion vector will be in terms of pixels, am I right? It should be in terms of pixel. If the motion vector is say 2 comma minus 3, if this is the motion vector, that means to say what? That I take a candidate block, and if I apply a displacement of plus 2 units in the n1 direction, okay, this is the n1 direction where we apply a displacement of plus 2 unit, and this is the n2 direction where I apply a displacement of minus 3 units. That means to say that I go by 3 units up over here. In that case, by applying this motion vector, I will be able to find out that which part in the reference image does it correspond to. Now, this motion vector elements are all integer elements, because we are estimating the motion as integer units, right. Now, think that what could be the problem of having integers. You see, what is the, how is the motion observed in the image? Okay. It is a real world movement, right. So, there is no guarantee that the real world movement will be restricted to the integer movement space. Your pixel resolution is there, you have a certain pixel resolution. So, I mean in terms of the actual movement, it is in the real space. Okay. So, I may be having a displacement of 0.1 units or 0.7 units or 0.77 units like that. So, what we are doing is that we are essentially, because we are spatially sampling the image and we are having some integer grid, okay, that is why we are saying that if it is 2.77, then I will be representing it as 3 units of displacement. If it is 2.03, I will be representing it as 2 units of displacement. Now, we can achieve some better accuracy if we go in for a subpixel accuracy representation. Now, it looks very odd that you may be immediately confused that how am I going to estimate my motion with subpixel accuracy? How am I going to, let us say for example, how am I going to measure my motion vector with plus minus 0.5 pixel accuracy, that is to say half pixel accuracy? Well, the simple thing what you can do is that you apply interpolation on the image. Okay. Whenever you are applying interpolation on the image, there are many techniques to apply interpolation. One can apply bilinear interpolation, or one can use some other nonlinear fitting algorithms. There are many such algorithms which are available in the image processing literature. So, essentially if you are incorporating some kind of interpolation, then you can increase the resolution of the image fictitiously. Okay. So, let us say that if you are having n by n image, okay, if your image size is n by n, then you can convert this into an image of space 2n by 2n. Okay. How? By interpolating. So, which means to say that if you are having a pixel here, a pixel here, a pixel here like this, okay, then it is possible for us to predict the pixels which are there in between. So, these are say 1 units. Okay. So, here to here it is 1 unit distance, but at 0.5 distance, okay, I can apply interpolation and get the intermediate values. So, all that I am indicating by red, okay, these pixels can be interpolated. So, you see original image was a 4 by 4 image, but the interpolated image is 8 by 8. In fact, there will be some I mean black pixels even here also. Okay. So, it is now increased, the resolution of the image has been increased to 2n by 2n. Okay. Now, if we increase the resolution and at the increased resolution we search for the block in the current frame with the increased resolution block in the reference frame, in that case okay, the displacement that I will get is in pixel unit, but in the enhanced space. So, which means to say that if the motion vector that I obtain is n1 comma n2 in the increased resolution space, then in the original resolution space my motion vector will be n1 by 2 comma n2 by 2. So, if n1 happens to be 1, then n1 by 2 happens to be 0.5. So, I can have sub-pixel accuracy. So, this is in this case a half pixel accuracy, and now this can be extended to make it quarter pixel accuracy, a resolution of plus minus 0.5 pixel, which means to say that I have to interpolate okay, to obtain 4 pixels within 2 consecutive ones. Okay. In the earlier case I was having 1 pixel in between another. Okay. In this case totally we must have 4 pixels. So, that an n by n image can be enhanced to 4n by 4n image by interpolation, and if we carry out the motion vector estimation in this space, then we get plus minus 0.25 pixel accuracy, which is a quarter pixel motion estimation. Now, let us see that what are the salient features that H.264 offers to us. Yes, questions?
Is this only done on the luminance space, or is it
Yes, very good question. Now, the motion estimation, I mean in order to do the interpolation you did not have to do it in all the y, CR and CB space, because after all the displacement is going to be similar in both y and CR, CB space. So, only one is enough, and in fact it is done in the luminance space only, because in luminance space if we do the motion estimation, then one can represent that to be the motion vector. Okay. So, luminance is done. So, now the improvement, so the salient features. So, let us list out the salient features of H.264 standard. So, the first is that it has a variable block size motion estimation. Now, this is a very important issue, okay, which I need to elaborate. Now, you see, so far I was saying that we subdivide the frame okay, into non-overlapping blocks of some fixed size. Fixed size means that that fixed size could be 8 by 8. Okay. So, it is all fixed size fixed block sizes it is partitioned to, I mean conventionally. So, this is 8 by 8, all of these are 8 by 8 block sizes. Now, let us first discuss that why is this 8 by 8, why not 4 by 4, or why not 16 by 16, or why not 32 by 32, who decides that it is 8 by 8? Well, if we make the block size to be very large, okay, what advantage do we have? First advantage is that okay, I mean if say for example, let us take some specific example. Let us say that the image size is 176 by 144 pixels. Okay. Say we use this size. In fact, this is a very standard size which is used in the small sized images. In fact, what you are observing in your video phone screens is of this size, 176 by 144, that is the typical resolution, that is what you have. Now, in 176 by 144 pixel size, this is referred to as quarter common intermediate format, or QCIF is the standard size that is adopted. Now, let us say that we have a block size of 16 by 16. Now, this means to say that so if we use 16 by 16 block size, then we are having 176 by 16 11, 144 by 16, that is 9. So, we have totally 99 blocks. If on the other hand we make the block size as 8 by 8, we are going to have 396 blocks. If on the other hand I have 4 by 4 blocks, then it will be 396 into 4. So, the 792 1584 blocks. Now, which one is better? Now, if I look at the number of bits consumed in estimating the motion vectors, then this is definitely the best, because only 99 motion vectors are to be transmitted. Whereas, if I use 4 by 4 block size, then 1584 motion vectors are to be transmitted, just how many, 16 times of this, 16 times this, those many motion vectors to be transmitted. So, naturally encoding the motion vector, this will consume much more number of bits. So, definitely from that point of view, larger the block size is, it is better for us. If we could make it 32 by 32, still better. But then what is the difficulty if we keep on increasing the block size? Well, there the difficulty is that whenever you are having a block based motion, you are having an inherent assumption that, as if to say, the whole block is moving, okay, with the same displacement. So, you are assuming some sort of a homogeneity within the block, or you are assuming that this particular block, okay, is a part of a rigid body which moves as a whole. Now, if that is so, then assigning a single motion vector for 16 by 16 blocks makes sense. Okay. So, like say for example, if I have an object like this, a rigid body object, and supposing I have subdivided the image into a set of 16 by 16 blocks like this. These are all 16 by 16 blocks. Okay. Now, you see this block is fully inside the object. So, if the object is having a displacement vector like this, this particular block is having that displacement, even the next block is also having, even all these blocks which are fully contained. But there are some blocks which you are observing which is having only a part of the object covered, like say for example, take this block. This part of the block is moving, but rest of the area is pertaining to the background. So, it is not moving. So, if I assign a motion vector corresponding to this object to this entire block, I am making an erroneous conclusion. I am imparting a false motion to the background area also. Okay. So, what is the solution? If instead of instead of assigning a single motion vector to the entire 16 by 16 block size, if I subdivide the block into 4 8 by 8 blocks, then I can assign motion vectors individually to these 4. Even here also you find that okay, here 0 displacement, here 0 displacement, here 0 displacement, but this entire 8 by 8 is going to have the motion vector corresponding to this part, which is not even engulfing 8 by 8 area. So, we can say that okay, this 8 by 8 area is a moving area, let me subpartition this area further into 4 sub blocks of 4 by 4. By doing that, I will be finding that it is only one of these 4 by 4 areas which is moving, okay, and rest of the 3 4 by 4 areas are stationary. So, only this particular block will be, so this block which is of size 4 by 4 to which a non-zero motion vector is assigned. Okay. Now, for the rest of the area what I can do is that for this entire 16 by 16 there is no problem, I can assign a single motion vector. For this 16 by 16 I can assign a single motion vector. That means to say that it depends on the parts of the image. Wherever any block corresponds to the boundary of an object, it makes more sense in subdividing that block into further sub blocks. So, that is the advantage that one gets as the variable block size motion estimation, meaning that for some parts you can keep 16 by 16 block size, for some parts of the image you can subdivide the 16 by 16 blocks into 8 by 8, for some parts you can subdivide into 4 by 4, this 8 by 8 could be subpartitioned into 4 by 4. So, it is a variable block size motion estimation, and not only that, the H.264 standard has got so much of flexibility that even whenever you are having a 16 by 16 block size, let us say that this is a 16 by 16 block size, okay, I can not only subdivide this into 4 sub blocks of 8 by 8 and have 4 motion vectors, I can also say that for this 16 by 8 there is one motion vector, for this 16 by 8 there is another motion vector. So, 16 by 16 can be partitioned into 4 different ways. If this is the 16 by 16 block size, say this is 16 by 16, then it is possible for us to have a vertical partitioning and have this we are going to call as 2 16 by 8, then we can have 8 by 16 by having horizontal partitioning. Okay. One can have 4 8 by 8 partitions. So, this is 4 8 by 8 partitions. Okay. And similarly, every 8 by 8 block, okay, can be partitioned into 2 8 by 4 blocks or 2 4 by 8 blocks or 4 4 by 4 blocks. So, this is the variable block size motion estimation. Okay. So, this is one advantageous feature which was not there in the earlier versions of the standards, it is there in H.264. Then there is another aspect, and that is the quarter pixel accuracy motion estimation. So, the second is quarter pixel accuracy motion estimation, the second feature of H.264. This I already mentioned. The third point is motion vectors over picture boundaries. Now, what I mean to say by this is that, say this is the candidate frame, okay, and we have some parts of the object. Now, here the motion vector could point outside the boundary also, means what happens is that this may be viewable in the part of the space, I mean in the reference frame, where in the viewing area of the reference frame you cannot find the object, but actually in the memory whenever you have stored the reference frame, then part of that is still available in the memory, but not in the actual viewing area. So, you can point out to those areas in the motion vector. Okay. The next feature is multiple reference picture motion compensation, multiple reference frame facility. Let me tell you that what is the multiple reference frame facility. See, we assume that we are just predicting the motion with respect to the previous frame, okay, or whenever we are doing a bidirectional prediction, there we are predicting with reference to a already predicted frame. So, whenever we are having B frames, there we are predicting it forward I frames or P frames, and the backward prediction we are making from some P frames, like this we are doing. But the frame references have to be fixed throughout the image. What I mean to say is that if this is a frame, okay, if this is the candidate frame and we are having a motion estimation with respect to the immediate past frame, okay, then what we are using is delta equal to 1. Delta equal to 1 means a delay of only one frame. So, that means to say that there every candidate block is searched, okay, with respect to the previous frame. So, delta is equal to 1, but in the case of H.264 what happens is that some of the macro blocks you can have a reference of immediate past frame as delta equal to 1, but for some frames you can define some different delta also. Like say for example, if I define this to be delta equal to 1 and I define the next macro block with delta is equal to 2, what it means is that for this macro block the reference frame is not this one, but what I have 2 frames back. Okay. So, there is a provision to have up to 5 previous reference frame. So, up to 5 previous frames, okay, can be accommodated and can be used as reference, may be used as reference. So, this is the multiple reference frame facility. Okay. Then another point where it has gained is the transform. So, the transform is actually an integer transform. Now, in all the previous standards, okay, they have used the DCT. Now, the DCT coefficients, as you know, that all the DCT kernel values, they are basically the cosine values. So, cosine values are real quantities which are represented within a value within a range of -1 to +1 real values. But in the case of the H.264, instead of using the real value DCT as the transform coefficient, a new transform which is referred to as the integer transform is defined, and integer transforms kernel is like this. So, its transformation kernel, actually the integer transform is applied on 4 by 4 blocks, okay, not on 8 by 8. In the earlier standards 8 by 8 was followed, as I mentioned in the JPEG also, okay, and even in the standards like the MPEG 1, MPEG 2, everywhere the block size is treated as the 8 by 8, okay. But in H.264 the integer transform is done like this, that it is a transformation kernel having these entries. So, this is the integer transform array, 4 by 4 integer transform array. Now, what do you observe in these elements? The elements are either +1 or -1 or +2 or -2. So, the elements can assume only these 4 values +1, -1, +2, -2. What is the advantage? Advantage is in the hardware implementation. You see, multiplication by +1 is a trivial multiplication. Okay. So, whatever value is there, you are retaining the same value. Multiplication by -1 means it is complementing the sign. Okay. It is just taking the ones complement of that. Multiplying by 2 means that you are making right shift by one position. So, hardware wise it is very easy to do, and multiplication by -2 means you are doing right shift, but doing a negation. So, take the 2's complement and do a right shift. So, that is why the integer transform can be very easily implemented in hardware, and they are using 4 by 4 block sizes. So, the hardware unit is very much simplified. The integer transformation computation is not involved at all, which is the case in the case of the earlier standards. Okay. Then another great advantage of H.264 is its directional spatial prediction, okay, for intercoding. What we mean by directional spatial prediction for intra-coding is like this, that you see, in the intra-coded blocks or intra-coded macro blocks, okay, what we do is that there is no prediction that is employed, no past reference can be used for the intra blocks or intra macro blocks. Okay. But in the earlier standards, that is why the intra blocks were, I mean, for intra coding the blocks were just treated as intra coded blocks, and there was no prediction that was employed. So, directly whatever intensity values are there, based on that the transformation was obtained and encoded. Now, it is seen that many a times the blocks, okay, which are to be encoded in the intra coding bears some very close similarity with the neighborhood blocks. The neighborhood blocks which are appearing above, or the neighborhood blocks which are appearing to the side, or the neighborhood blocks which are appearing on the top left diagonal. Okay. These blocks could be used for predicting the coefficients of the intercoded blocks. Okay. So, it is done something like this, that supposing we just have a 4 by 4 blocks like this. So, supposing this is a 4 by 4 block, okay, which is to be intra predicted, which is to be intra coded. Now, one of the way whereby we can do is that we can take the 4 pixels which are there immediately on top of this block, this pixel say A, the pixel B which lies just above this, the pixel C which lies just above this, and the pixel D. Now, I can use these 4 pixels A, B, C and D to predict this intracoded block by simply copying this A's intensity values into all these 4 positions, by copying B into all these 4 positions, by copying C into all these 4, by copying D into all these 4. So, in this case this is a vertical prediction. So, we are using the top pixel to predict this 4 by 4 block, and this is vertical prediction, and vertical prediction is called as the mode 0 prediction. So, just like the way one can do a mode 0 prediction, one can do a horizontal prediction also. How? Let us take 4 pixels on the side. Let us take the pixels E, F, G and H, E, F, G, H, and we use the value of E in all these 4 pixels, use F in all these 4, G in all these 4, H in all these 4. So, in this case it is a horizontal prediction, that is what we are doing, and this will be referred to as mode 1 prediction. Okay. In fact, there are 8 different directions that are employed, okay, in the directional prediction of H.264, and the 8 different directions are like this, that this vertical one we are calling as the mode 0, the horizontal we are calling as mode 1. Okay. Now, mode 2 is a very interesting one. Mode 2 is actually what is known as the DC prediction. DC prediction means that the average intensity value is used to predict the next frame. So, it is not a directional prediction to predict the block. Okay. So, it is not used in the direction, but the direction 3 is used in this. So, direction 3 is this one, propagating 45 degree, direction 4 is this direction. Okay. That means to say that predicting from this one. So, this is direction 4. Okay. Direction 5 in between direction 0 and 4. Okay. Direction 6 is in between 4 and 1. Okay. All these things are 22.5 degree apart. Okay. Direction 7 is in between 0 and 3, and direction 8 is this one, 22.5 degree above this. So, totally 4, 5, 6, 7, 8 different directions, 0 to 8. Mode 2 is used as the DC prediction, but mode 0 to mode 8 are used similarly for predicting from different directions. So, just like the way I talked about mode 0 like this, mode 1 like this. Okay. If you look at mode 4, then mode 4 will be a diagonal propagation. Okay. Mode 5 will be with a 22.5 degree, means again I mean it will get propagated in some manner like this, that not all the pixels will be diagonally propagated, it will be sampled and made into 22.5 degree directions. So, these are some of the salient features of H.264. Okay. Next class I will summarize the coding technique of H.264 along with 1 or 2 examples. Okay. Thank you.